Let us look at proposition number 13 of book 4 of Euclid's Elements. The proposition talks of constructing, or more appropriately, inscribing a circle in a given equilateral and equiangular pentagon. So let's see what we can do. The first thing is we have to find the center. Okay, so for that what we'll do is we will bisect angle BCD. We'll bisect this angle and we'll bisect this angle. It's not necessary for you to bisect only these two particular angles. You can bisect any two angles. Okay, we know how to bisect it. So let's do this. Okay, and the second one I'll just directly mark it. And let's hide all these elements. The intersection of these two lines, let's say F. And now we don't need these two. Now let's join CF, DF, BF, AF, and EF. Now remember, using a previous proposition, we bisected this angle BCD and CD, right? So we know that this segment FC and FD bisect BCD and CD. But what about the other three? We just joined BF, AF, and EF. So we have to prove that these segments also bisect these angles. Okay, so let's see how we can prove that. Because FC bisects BCD, we know FCB is equal to BCF. We know FC is common to both the triangles. And we know BC is equal to CD because this is a regular pentagon. So which means these two triangles are congruent based on side angle side. Which means all the corresponding sides and angles are also equal. So angle CBF is equal to angle FDC. But remember, this angle, FD line segment also bisects CD. Again, based on the previous proposition, we bisected CD, which means if we take angle EDC is going to be twice the angle FDC, which means ABC is also going to be twice the angle CDF. Why? Because angle CDF is equal to angle CBF. So since these two angles are equal and this is twice this angle, that means this is also going to be twice the CDF. That means these two angles are equal to each other, which means we can follow the same logic in a circular pattern and show that all these angles are equal to each other. So here the critical thing was, you might say, okay, anyhow we know it is a regular pentagon, then naturally it is going to be, these angles are going to be equal because we have given that it is equiangular. But then remember, as part of construction, we bisected these two angles based on a proposition which we have already proved. But these lines, we just joined them. So we have to show that these lines also bisect these angles. Okay, now that we have done this, because now we have to take up the next part, and that is constructing a perpendicular to BC from F, perpendicular to CD from S, perpendicular to DE from F, and like this for all of them. So we know how to do that. So let me do it for one and then I'll just mark. Now let's hide off all these and let's join H. Let me just draw the others since we know how to do it. Now we have to show that all these are equal to each other. So to show that all these lines, the dark GF, MF, LF, KF and HF, they are all equal to each other. Let's take these two triangles, triangle HFC and CFK. We know FCH is equal to KCF because remember, as part of construction, we bisected BCD using CF. Now CHF is equal to FKC. They are both right angle, and FC is common to both the triangles. That means angle side proposition, we can say that these two triangles are congruent. And since these two triangles are congruent, we can say that HF is equal to KF. And similarly, we can go around and prove that HF equal to KF is equal to LF is equal to MF is equal to GF. Now what we do is, taking F as the center and any one of these segments as the radius, and we draw a circle. So this would be the required inscribed circle, inscribed in a given regular pentagon. So that was proposition number 13 of book 4 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail with proper references to the previous propositions what I keep talking of. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share it. That's it for now.